So just a few comments about what we did last time. So about the deterministic theory. So just to remind you, we saw that if you have a graph circle packed that is with a bounded degree covering the entire plane, or what we call the carrier of the graph of the circle packing equals R2, then this graph is transient. And otherwise, if it's circle packed inside the unit disk, it is transient. And in the notes and in the nomenclature in the papers, these two things are called CP for circle packing, parabolic if it covers all the plane, and hyperbolic if it's contained in the disk. And I showed you the proof, and I just want to add one remark about what we actually one remark about what we actually showed, and then a few comments, because many of you have asked me about further theory, what is known in the literature. So one comment is what we actually proved in the recurrent case. So we proved not only that the graph is recurrent, but we also gave a quantitative bound for the recurrence, for the growth of the effective resistance. And this is why I chose to show it to you via electric networks, because in the original Heshram theorem, it's a little difficult to obtain this quantitative bound. So what we've shown, in particular, in the recurrent case, we showed not just that the resistance goes to infinity, but if you look at the resistance between rho and all the vertices outside of the Euclidean ball of radius r, not the graph distance ball, right? The Euclidean ball of radius r, this grows at least like some logarithm of r, right? So c times log of r, right? And I'm reminding you the argument, right? We had this ball of radius 1, which is the root, right? And here we have the Euclidean ball, which is of radius r, right? So we're putting here log many annuli, dyadic annuli. So perhaps this is a 2, this is a 4, and so on. And the resistance across each of the annuli is at least a constant, right? There are no edges between two not consecutive annuli, but just one after consecutive annuli. So you're allowed to add all of these resistances and get a lower bound, right? So because we have log many annuli, we get a logarithmic bound here. And this will be very useful as well today, because this is a bound that you can apply in all kinds of scales, right? Not just in this particular one. So for instance, if you have a teeny weeny circle here of radius epsilon, right, and of constant distance from the origin, right, and you want to find the resistance between these two vertices, right? So let's call this, for instance, v epsilon. Then the same kind of argument shows you just by putting annuli here, etc., etc. The same kind of argument shows you that the resistance, right, between rho and v epsilon, under indeed the condition that this is of size epsilon and that the distance is at least a constant. By the way, the distance has to be at least a constant. Why is that? Constant that does not depend on epsilon. Epsilon is small. If the graph has bounded degree, because the ring lemma, right? This vertex cannot be a neighbor of this vertex, right? Because it would be too small. The ratio would be unbounded. So this vertex rho has to be surrounded by at most 10, right, other circles of bounded degree. So it makes the distance at least a constant. So you can put enough annuli there, as long as, of course, everything is everything is filled. But in fact, you don't even need that you have other circles inside, right, because of monotonicity of the resistance. So this would be bigger than a constant times log of 1 over epsilon, right? So is the fact that so it should be clear that it's exactly the same type of arguments that we use for estimates like this, and we will use it today, Okay, any further questions about these type of arguments? The arguments, again, are constructing a harmonic function to give a lower bound on the resistance, or constructing a flow to give an upper bound on the resistance. So a few remarks about developments or further theory, if you're interested, with no proofs. So the first thing is in the transient case, or in the CP hyperbolic case, right? It is a theorem of, so I said that, but I'll say it again. Not only does the random walker not return to the origin, it converges to a point on the boundary. So this is a theorem of Binyamini and Schramm. Of the late 90s. The random walker converges also, almost surely converges. So this is the hyperbolic case, but also bounded degree. Right? And I mentioned that if it's not bounded degree, there is a possibility that the random walk spirals as it gets closer to the boundary. The random walker almost surely converges to a point on the boundary of the unit disk U, right? And and this exit measure. So if you know that it almost surely converges, you could talk about what is this point, and so you have a measure on the boundary of the disk, and this measure is non-atomic and has full support. The exit measure is non-atomic. It has no atom, non-atomic, and has full support, meaning that every interval you have a positive probability of exiting through it. Non-atomic and has full support. Right, so for those of you who know what we know what harmonic functions are. So you can ask, are there bounded harmonic functions on this graph? And the answer now is yes, right? Because you have, if you have here your circle packing of the graph, and it converges to all the to the unit, it's packed inside the unit disk, then you can take any interval on the unit disk, some interval I, and your harmonic function could be h of x. This is I, is the probability starting from x that the random walker is swallowed in I, or exits at I. Right, that it converges, that the point that it converges is somewhere in I. And this is an honest-to-God harmonic function. It's non-constant. You have to prove that it's not constant, of course, and right, you have to show that if you're very far away from I, right, if you're somewhere here, this probability is going to be close to 0, and if you're somewhere close to I, then the probability is going to be actually close to 1. So it's not constant, and it's obviously bounded, and this is so there exists non-constant bounded harmonic functions. And in fact, what they show is that it's clear from this type of argument that, of course, you don't just have one. You have, for any interval, you have such a function, and any mixtures of these things. So in fact, if I give you any bounded function g on the, so in fact for any g from the boundary of the disk, from the unit circle, that gives real value and is bounded, and you also have to say that it is measurable, it extends to a harmonic function inside the graph, right? And the extends to harmonic h from G to R, simply in the same way, the value of a function, the value of the function h at a point x is the expected value of G at the exit point of the simple random walk. right? And this is as long as G is bounded, this gives you a whole class, an infinite dimensional class of harmonic functions. And in fact, in recent work, so this is due to Omer Angel, Martin Barlow, myself, and Ori Gurel-Gurevich, that I'm just going to write GG because it's too many letters. We proved that these are all the harmonic functions that you could obtain. So there are no other harmonic functions, bounded harmonic functions. And I just want to emphasize that this is a statement. You know, what does it say about the random walk? It somehow says that aside from knowing where is your exit point, there is no other invariant or infinite information contained in the behavior of the random walk. So for instance, if I know that I converge to this point, if I somehow condition on this event, then it cannot happen. So this statement, so this is, what year is this? It's 16, but it just took it a long while to be published. This is from 14. So the probabilistic meaning of a statement, there are no other harmonic functions, is a statement that there is no other information about the long-term behavior of the random walk. So for instance, if I condition on my random walker to exit from this point, this is, of course, an event of measure 0 because there are no atoms, but you can imagine that you can condition on such a thing by taking the limiting conditional measures if I take a small enough interval, and such a thing indeed makes sense. So the statement is that if I condition on exiting from this point, I cannot have an event that occurs with probability half, for instance, to be converging to it from the right or from the left with probability half, right? There is no, so such a behavior of the random walk cannot exist. It has to go from all directions or just from one particular direction. All other events, all other invariant events conditioned on the exit location have to be 0-1 events. And this is the contents of this theorem, and if you're interested in it, you can read it. Another corollary that follows from this Binyamini-Schramm theorem is something that tells you something very interesting about planar graphs. So a corollary is that if you have any bounded degree planar transient graph is non-Liouville. It's what's called non-Liouville, meaning there are non-constant bounded harmonic functions. So this is a corollary, and I'm not telling you exactly how to prove it. It is clear that in the triangulation case of bounded degree, this indeed follows. This is just this statement, but in fact it follows for any planar transient graph, such as the regular tree or anything that you may invent. And you indeed need the bounded degree assumption. Can anyone give me an example? You know, I'm looking for a planar graph that is transient, but somehow I know exactly what's going to happen to the random walk. There is no... Sorry? Right, exactly, or something of this form. So if I have a biased random walk that goes in a particular direction, for instance, one edge here, two edges here, four edges here, and so on. This is a planar graph here. I've drawn it to you. It is obviously transient, but there are no, you can think about it, why there are no bounded harmonic functions. In this case, it's actually very easy to prove because it's a very well-known random walk. You always converge in this direction, and there are no other 0-1 events. Sorry, there are no events that have a non-trivial probability that talk about the infinite behavior of the random walk. Okay, so this is so this is one extension to the CP hyperbolic case. that if you're interested, you can read about. There's another extension of this Heshram business in the case that we are not a triangulation of the plane. So all of this theory relied on the fact that we are a triangulation of the plane, meaning that the graph is one-ended, right? If you remove any finite set of vertices, what's outside has only one infinite component, right? But we already saw a graph that is not like that, the tube, right, which has one accumulation point and is not infinitely ended. Sorry, it's not one-ended, it's two-ended. What happens if you have a very strange set of accumulation points? If, for instance, you have a Cantor set, right, so let's draw. Okay. It's hard to draw a Cantor set, so let's just say this is the Cantor set and imagine that it really is. And you have a circle packing of some graph that covers all the plane except for this set, and it converges to this set. Can you determine if this graph is transient or recurrent? And this is a theorem, again, that I will not prove to you, but all of these things use in some sense the same methods, effective resistance, and perhaps some other ideas and tricks, and they are all things that work in the completely deterministic bounded degree case. So the theorem is as follows. So if G is a triangulation, bounded degree, and P is a circle packing, of G, and A is the set of its accumulation point. So an accumulation point is simply a point in the plane in which every neighborhood of it intersects infinitely many circles. Right? So it's just what would naturally be an accumulation point. So if we're in the CP hyperbolic case, in this case, the set of accumulation points is just the unit circle, right, the boundary. And if we are in the parabolic case where the circle packing is all of R2, then our set of accumulation point is just the empty set. And the theorem is as follows. G is recurrent if and only if A is a polar set for 2D Brownian motion. Which means that A is a set that if you start two-dimensional Brownian motion in the plane outside of this set, you will not intersect it with probability 1. So every set in the plane is either polar or not, and this gives you, in fact, a precise criteria. A is a polar set for 2D Brownian motion. So just standard Brownian motion in the plane. Right? So in particular, and this is a theorem due to Ori Gurevich, myself, and Juan Soto, who's a topologist from Rennes. So in you can think about why this theorem is true. It gives you a complete criteria when you're in the case of a triangulation on how to determine whether the graph is recurrent or not. And in particular, you get the Heshram theorem, right? If this is, of course, this set is non-polar for Brownian motion, right? Brownian motion on the inside will hit it. And so the random walk will be transient. And the Cantor set that I drew here, depending on its dimension or its length, you can determine whether it's a polar set or not. There's a classical theory due to Kakutani how to determine whether a set is polar or not via calculation of capacity, and you can figure out for which Cantor set the corresponding triangulations would be recurrent or transient, and this gives you a complete answer in the case of a bounded degree triangulation. Right? And if you know what happens in the unbounded, if you want to know what happens in the unbounded case, then you should talk to my postdoc Daniel or Ori's student Matan, who's somewhere here, and perhaps come to their talks on Monday. Okay, any further questions about this before we start talking about random planar graphs or random graphs in general? Okay. So as I mentioned several times, of course we could continue talking about this, but things become more interesting when the underlying graph is random in itself. And so of course we cannot hope for such a beautiful theory to hold in the random case because well, it depends on what kind of randomness we allow ourselves to consider, and but in the case of a random planar map, or in the case, and what does it even mean, a random planar map? We saw some examples perhaps in the first lecture, but one simplest case of them all is you take a sequence of finite planar maps, and each time choose a random uniform vertex to be the root. You look at the local limit which we will formally define right now, and it turns out that the theory, the hyperbolic part of the deterministic theory is almost irrelevant. If you take such limits, in almost all the cases, you will get a parabolic limit. So when you try to pack it, it will always be packed inside almost the entire plane. Okay, so this is a very deep yet completely elementary theorem of also Binyamini and Schramm, but not in this paper. This is my goal to prove to you today that in some setting, when you deal with random plane with local limits, you never reach this hyperbolic case, which is somewhat surprising when you see it, at least for the first time. So what is a random or local limits of graphs? So let's first talk about convergence of graphs. We mentioned this in the very beginning. Let's do it slightly more formally now, right? Yes, question, Sebastian?
Sorry, it's a question about 2 minutes ago, but is it possible for triangulation to have a set of accumulation points that is a contour? Or?
That is Cantor? Yes. In fact, it is possible for any set that you give me, there is a triangulation that accumulates to that, and that's simply start drawing it, right? Simply, do a greedy algorithm. Every time you have a drawing, add another circle. You can always add more and more circles and avoid the set of points that you want. And you can always do that so that you exhaust the entire space that you have not drawn that is outside of this set. So in fact, any set is possible to obtain.
Closed set, maybe.
Oh yes, it has to be a closed set. Thank you. Sorry. Yes.
Triangulation. Okay.
Yes, with a triangulation and with a circle packing, and while keeping bounded degree. Okay. Yes. Okay. So convergence of graphs. So we're the local limits of graph falls under the big theory, the usual theory of convergence and distribution, but of random variables. But we have to speak about what is the space that our random variables receive values on, right? We all know this theory for perhaps what we learned in the very basic beginning is convergence and distribution on R, but we understand that this does not, not only the real numbers are there. So the space in which a random variable will take values is what we call G bullet. And this is the space of rooted, locally finite graphs. So that means that each element of the space is a graph, right? So each element is a graph and a vertex row of this graph. I call row the root, but I can, of course, give it any other name. So this is an element. Here you have a graph. All it has to be is locally finite. It could be infinite. It could be finite. It doesn't matter for the space. And row is a vertex of the graph. So G is a graph, and row is a vertex. And we not just look at these as elements, but we consider them as equivalence classes. Okay, so two elements are equivalent, so G1 rho 1 is equivalent to G2 rho 2 if there's a graph automorphism that takes rho 1 to rho 2 and G1 to G2. So this is if and only if. The graph automorphism, I'm reminding you, is a mapping that is a bijection between the vertices of G1 and G2, such that every edge in G1 moves to an edge of G2, in the same way that Sebastian talked about last night. So this is if and only if there exists phi from G1 to G2 automorphism such that phi of rho 1 equals phi of rho 2. So in this case, you see that if you look, if for instance you're looking at the binary tree of height n, the finite graph, right, and so on. If you take this graph and take this vertex to be rho, this is exactly the same element as taking this vertex to be rho, right? These graphs are completely isomorphic, right? Also, if you have an infinite graph of the form something like the canopy tree that we've seen before, right? What we will show, or what we already know, is the local limits of binary trees, right? Et cetera, right? Putting the root here or here or here gives you exactly the same graph in this space. Okay, so we have a space, and we want to take random variables taking values in this space, so we want it to be a Polish space. So we want to, we want to induce, to put a metric on this graph such that the resulting metric space will be complete and separable. Okay, so this is just this abstract nonsense. So let's do it one time properly, and then not discuss it anymore. So we induce a metric, right? We define a metric. The distance between G1 rho 1 and G2 rho 2, right, is 1 over R, where R is the largest number integer such that the ball of radius r around in G1 around rho 1, the graph distance ball. So I look at all the vertices and edges that I can reach from rho 1 within a path of length r, and look at the induced graph spanned by this. This is isomorphic as a finite rooted graph to the ball of radius r in G2 around the second root. So such that the ball in G1, this is going to be my notation, and there's always going to be confusion between when I'm writing Euclidean balls and when I'm writing graph distance balls. And I'm going to try and make it. I'm going to try to make it clear, but the honest truth is I'm always confused by this notation as well. So it should be clear by the context. The ball in graph distance, so that's why I'm putting the graph here around rho 1 in R, is equivalent as there's a rooted graph automorphism as there is here to the ball in G2 around rho 2 of R. Okay, so as R is bigger, then that means that locally, from the point of view of rho 1 and rho 2, the graph looks the same up to distance R. And now you can convince yourself that this is indeed a Polish space. What are the graphs? So closeness is not so bad. Why is it separable? What are the bases to this topology? It's all the finite graphs, right? All the finite graphs span everything here, because every infinite graph you can approximate essentially by in this way, in the metric way, by a finite graph. Let's do a little sanity check. Is this metric space compact? Yes. Why? Oh, I mean, no. because you nodded. But yes to your nodding. Why is it not compact? Yes?
Can take a star with a...
Right. I can look at the following set of graphs, right? Finite graphs, right? The row has degree 1, on the other it has degree 2, right? And at the nth one it has degree n, right? And so forth, right? So this sequence of, this set of graphs does not have, or this sequence of graphs does not have a converging subsequence, right? Just because the degree at the root blows, right? And in fact, you can convince yourself that it's very easy to figure out when is a subset of this space pre-compact. You just have to control all the degrees all the time. So this is I don't want to delve too much into this abstract nonsense, but the point is that now, so this let me just write the statement that this is a complete separable metric space or Polish space. So it is a fact that this is G hat is a Polish space. And let me just say that so this is the space that we're going to draw random variables at, but this is not the only space, I'm afraid, that we're going to draw the random variables at, because we want to do all sorts of other operations. For instance, we want to draw a random planar map and not a graph, right? So how do we also draw that? So now there's a set of things that you could do that are pretty straightforward to extend this space. So for instance, instead of looking at rooted locally finite graphs, right? We will look at rooted locally finite maps, right? And call this space perhaps, okay, so let's change color. This will be maps. I'm reminding you, maps is a graph, a planar graph, but also that has a cyclic orientation. For each vertex, it has a cyclic permutation of its neighbors. So in this case, we will look at the space M dot. The dot, the bullet here, represents the fact that it is rooted. And then we have to define what does mean to be automorphism between maps is going to be the same thing. You know, a map moves the vertices. It's a bijection between the vertices such that the root goes to the root, and the cyclic permutation, right, in the original map and in the target map is maintained by this phi, by this bijection. So this would be a map automorphism instead of a graph automorphism, right? And then we can define everything exactly the same thing. So here we will have and here we will just say largest integer such that this equivalence is a map automorphism instead of a graph automorphism. Okay, so this is one thing. This is also mentioned in your notes. And we will also want to do things that are even more complicated. What if you also have a set, and this we will actually, or perhaps in some unfortunate way, need to use this fact that you could do it. What if you also allowed to put labels on the edges? So you're allowed to put a real number over every edge in this class, right? And you want to take this space as well, because you want to take random variables that are not just random maps, but also random maps that receive a certain number on a real number on these edges. So I claim, of course, I don't want to define this to you again. This is all defined in your notes, perhaps in chapter 6. But you can also define randomly rooted, locally finite maps with labels on the edges, right? And then just to keep this an open set, so an automorphism will be obviously the same thing. You know, the map moves. The map has to preserve the labels on the edges, the infinite automorphism. But just to make sure that this, there's a slight change in the definition here that we say that R is the largest integer such that this holds, right? So here you will have a map automorphism, but you don't want the labels to be equal precisely. You want them to be 1 over R away from each other, right? Or something like that in order to keep the space that you get, you want it to be an open set in some sense, or that every neighborhood is an open set. Right, so there's a way to also draw random variables and talk about convergence and distribution, not just for rooted graphs, but also for rooted maps, and also for rooted maps that have some information on their edges. And this information, by the way, doesn't have to be just a number in R, but it can be in almost any space that you could put them. So you can, of course, you could put many information on this. On these edges. But for now on, we'll just deal with random graphs or maps, and later we'll just recall for next week that we're also allowed to keep other further combinatorial information or whatever information that we want. For instance, we could draw just random numbers on the edges, and we want this to to converge or to discuss about convergence and such a thing, and we are allowed to keep all this information. Okay, so now that we have a Polish space, and all of these spaces, no matter what you have, are going to be Polish, and it's okay to talk about convergence and distribution. So as usual, we say that xn, right, a random variable taking values in this space converges to x in distribution, right? If for any function from G, so I'm just going to write G bullet instead of all of the other spaces that we can work with. If any function from G bullet to R that is continuous and bounded, the expected value of f of xn converges to the expected value of fx. Right? So for instance, f could be the degree of the root vertex. Okay, so and when we so this is what we mean and this is what we call convergence and distribution, right, in this set. So these are random variables in some probability space taking values in this G hat. And now we're in a good position to take. So our random variables are going to be almost always yes, question?
Has F to be invariant from graph homomorphism?
Sorry?
Has F to be invariant from graph?
Well, F is defined on G star, on G, not star, on G bullet, right? So F has to give the same value to this graph rooted here or rooted here, right? It's defined on equivalence classes of graphs. So the answer is yes. What will be our random variables that we take? There will be two kinds, or one kind, in fact. You have a sequence of graphs, a sequence of finite graphs, Gn, and xn is simply going to be the rooted graph. So in our typical example, Gn is a sequence, or is finite graphs. Right? And we're going to choose rho n to be a uniform random vertex in Gn. Right? And this defines an honest-to-God random variable in this space. Right? So Gn is a sequence of finite graphs. And now we are ready to define. Now we have established the enough abstract nonsense so that all of the words in the following definition will make sense. So the definition is the following. Gn is a sequence. So here, finite graphs with random root. So when you take this example and you figure out what this convergence and distribution means precisely, you will see that it is equivalent to what I'm writing right now. Gn is a sequence of graphs, of finite graphs. We say that Gn converges locally converges locally to a random, not necessarily infinite, but a random rooted graph, to a random rooted graph G rho if and only if for any radius, for any r, when I look at the ball around Gn, the graph distance ball around Gn with rho n, when rho n is the uniformly chosen root, chosen vertex of Gn, of Gn, you look at the ball of radius r around rho n in Gn, this converges, this is an honest-to-God random variable, so we could talk about convergence in distribution. This converges in distribution to the ball of radius, ball in G around rho of radius r. All right? And let's make a few observations. So for instance, we saw this example in the first lecture. If you have a finite line of length n, this converges, in this case the limit is deterministic, right? It converges to just the infinite graph z. And with z, it doesn't matter where you put the root, right? They're all equivalent, right? So this random variable is supported on a singleton, right? Well here, when you take the sequence of binary trees of length n, right, is the limit a singleton? Right, so what is so we saw that the limit is this infinite canopy tree, right? So you always get the same graph, but is the limit random variable supported on a singleton element of the space G bullet? No, right? Because the location of the root is undetermined. So you'll have this graph, the exact distribution of the limit it's always the same graph, right? But the root could be here with probability 1/2, right? And it doesn't matter which leaf, right? They're all the same element. Here with probability 1/4, and again, it doesn't matter. All of these vertices look the same, right? So they are the same element. And here with probability 1/8, and so forth, right? So it's the same graph, but a different root every time. So this is not a singleton. Okay, and we saw, did we see several other examples? No. And let's make just one more comment that I won't write down, is that let's notice that this definition works perfectly fine, not only if Gn is like in these examples, is a deterministic sequence of finite graphs, for instance, binary trees of height n, but also if you draw Gn according to some, with extra randomness, right? You draw Gn with some, according to whatever random rule that you want. You have some bigger probability space that also draw Gn in addition to this random vertex rho n, right? If Gn are deterministic, rho n is the only source of randomness. But if Gn are random themselves, you still have a different random variable, right? This object is a random variable over a bigger probability space, right? Receiving values in the same space, right? So everything here works, right? Everything here is well defined. In particular, when we will take Gn to be a random planar triangulation on n vertices, this will make perfect sense, right? We look at the whole distribution after the two drawings. First you draw the graph, then you draw rho n, right? And all we know is that given the graph, rho n is a uniformly chosen random vertex. Okay, and then it's a random variable in our space, and it makes perfect sense to talk about such a limiting object. Okay, so that's the only point that I wanted to make, that this setting works both when your sequence of finite graphs is finite and infinite. Are there any questions about this abstract nonsense? Why is it nonsense?
No, it's okay. Just to be explicit, this definition is the same if we take for every R like this, or if we take the definition on the left, right? Like Gn rho n converges in distribution to G rho is the same as asking for every R, blah, 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 right?
Yes. Yeah, so in fact, yeah, it's enough to check these for the indicators. For the indicators of graph, yes. Yes. Any further questions? Okay. So let's state the main theorem that I hope to prove to you today and perhaps a little bit on Monday. And this is a theorem that, as I promised, tells you that when you're dealing with such limits and your assumption is that the underlying graph is planar, you cannot be in the hyperbolic case. Okay, so this is the theorem of Bignamini and Schramm. And it's hard to estimate how influential this paper is. It's one of their most cited paper. And in fact, there's so many citations to this paper, not because of the result, but mostly because that they are the first one to define this type of convergence. And this has become extremely useful type of setting, an abstract setting to consider when talking about not just probability, group theory, and many other, and computer science, and many other things in many other disciplines in mathematics. And actually, the minority of the citations of this paper actually quote the theorem itself that they prove, right? Because this, as you can see, this setup, there's nothing special about planar graphs here, right? This applies to any. You can think about any non-planar graphs here, right? And this, and this is well defined. But the theorem is what I want to discuss today. Bignamini, Schramm, 91. 01 is the following theorem. Let Gn be a sequence of finite planar graphs with bounded degree such that Gn converges. So I'm not going to say locally, but I mean here locally in this sense to some infinite random rooted graph. It doesn't even have to be infinite. Converges to U, so let's call it, G rho. So it's a Gn converges. Then then G is almost surely recurrent. Recurrent for, as usual, the simple random walk. Okay, so this is a surprising theorem, or at least in the beginning it looks not something that you would anticipate. So even if you, so firstly let's just comment, even if you start with completely deterministic graphs, of course the limit can be random, just like we saw in the canopy tree. So I have to say here the almost surely, I have to say it even if I start with a deterministic setting. And what this means is that, for instance, you cannot have a sequence of graphs, of planar graphs, that converge to the binary tree. Right? It cannot happen. What does it mean for a sequence of finite graphs to converge to the binary tree, or to a deregular tree? It just means that your sequence of graphs is, for instance, the degree of every vertex, or almost every vertex, has to be d. And also when you look at radius 10, right, for n large enough, what you see is a deregular tree for height 10, right? And if you choose 10 to be any number, right, then from n large enough, all of the neighborhoods of that distance will look like a binary tree. So this only means that this sequence of graphs that converge, if they converge to a deregular tree, that means that for every vertex, for almost all the vertices, the girth, right, the size of the shortest cycle in the graph has to grow to infinity. And this is an if and only if condition that tells you when a graph converges to the deregular tree. There it's very easy to determine. So what this means is that there cannot be a planar graph sequence that converges to the three regular tree. There is no sequence of planar graphs that are three regular in which the girth goes to infinity. Right? It's not an immediate thing to see, right? If you try to construct such a thing, you put a bunch of vertices, you put trees, you try to connect it somehow in a planar way, you cannot do such a thing.
How about allowing two-dimensional surfaces but not the plane with some genus?
So this
with fixed or bounded genus.
If the genus is bounded, then this theorem applies as well. If you allow the genus to grow, then it's a different story. Okay. But let's just deal with the genus 0 case, because I'm tired and sick. But this is at least, this is a completely combinatorial statement that follows from this. But in fact, this statement is, there are other methods to prove it that are more direct and more interesting. And this is one of the one of the manifestations of this theorem, but this theorem is much stronger. In your page 52 of your lecture notes, you will see an example why this theorem has to have the bounded degree assumption. Right? And you can imagine this is the picture there, the figure up on the top of the page is a depiction of what is the infinite graph that you obtain in the limit, and you have to think about what is exactly the sequence of bounded degree planar maps that give you this limit, but this is what you get, and as you can see, this is a transient graph, right? It has one infinite branch in which the conductances are 1, 2, 4, 8, 16, so it has a subgraph that is transient, so the whole graph has to be transient. What else? What other comment did I want to make about this thing? You have to have bounded degree. We have an example, and I'll start by proving this theorem to you, and later we will see what do you have to do to make how can you extend this theorem when you don't have the assumption of bounded degree. Are there any questions about the theorem? Okay, so let's start proving it. The proof will be, to me, this is one of the beautiful, mysterious proofs that I've seen. As usual in this class, everything will be completely elementary, but of course it doesn't mean that it's easy. And here is the main estimate that we will need to prove. This is one of the most unnatural sounding statements that I've encountered in math, and the proof is even more strange. But everything works, and because of this, because I'm not the only one who felt this way when they first read this proof, this was dubbed by many people as the Binyamin Shram magic lemma. And this is the statement, and let's start and discussing it. So we have, the statement has no probability in it. It's just a completely geometric counting statement. You have a set C, a set in R2, a finite set of points. Finite set of points. And for each point, all right, so perhaps I'll draw some points on the plane, on the board. Right, for each point, you define the radius of isolation of the point. So the radius of isolation, rho w, is simply the largest radius that you can put around this point, so that the circle of this, the disk of that radius does not touch any other points. Right, so here you will have, this will be the radius of isolation if this is w. Right, so rho w is just defined to be the minimum, the distance of the minimal distant point to w. So it's the minimum of v minus w. V is in C, but not w. Okay, so this is the first definition, and then perhaps I should tell you before I make the next definition. I'm going to tell you how are we going to use this lemma without even knowing it, right? So by now we've developed all sorts of methods to prove that things are recurrent or transient. In particular, for planar maps, we know we have a great criterion, right? If you can circle pack them in the plane, they're recurrent, and otherwise they're transient. we want to show that something is recurrent. So of course, what we're going to try and do is take the circle packing of Gn, right? And to take in the same form that we showed by this compactness argument, take a limit of it and say, okay, what we get in the limit is the circle packing of G. And this is no problem. This will work. But now we have to argue that the circle packing that we see of G is not contained in some bounded space, right? In fact, it will it will exhaust all of the plane, right? And this will be the consequence of the lemma, except for one caveat that will be annoying for us, is that it's not going to necessarily cover all of the plane. Rather, it's going to cover all the plane, perhaps minus 1 point. Right? And why do you have to have this minus 1 point is annoying is because we already saw an example of a graph that you could obtain as a distributional limit in which the circle pack as a local limit, sorry, sometimes I say distributional limit or local limit, but these are synonyms, as I said in the first lecture. We have a graph that could be obtained as a local limit. In fact, it's a deterministic graph that when you circle pack it, you see a point in the in one accumulation point, right? That was what we call the tube, right? We have 3 circles surrounded by 3 circles from the outside, and also inside you have 3 other circles, and so on, right? This is a one-dimensional graph that you can obtain as the local limit simply of taking big chunks of it, right? You take the graph from height n to minus n, take all that graph. All the vertices look the same except for the edges, so when you choose a random point, you will not be close to the edge, and you will converge to this infinite graph, the tube. So we cannot hope that the statement will be the circle packing of this, the carrier of it is all of the plane, but what we will prove is that the carrier of this circle packing is a plane minus a point. Right? And this is already good because I claim that even when you have a plane, the carrier is a plane minus a point and your bounded degree, then you are recurrent. Why is this true? Okay, that's without using a more sophisticated theorem. So I'll let you think about it. And the way to, it's not an immediate argument, but right, you can cut a little circle around the accumulation point, right? And then you dismantle your graph into two infinite subgraphs, right? And the first one is everything that, so the first one, so here you have a circle packing, right? And you converge to one single point, right? And it covers everything aside from this point. So it covers the entire board aside the point. And here are some circles around the point. I'm not drawing everything inside, but it has just one accumulation point. So I'm going to take a little circle, an Euclidean circle, not a circle in the packing. Right? And I'm going to cut all these vertices, all these circles. There are finitely many circles that intersect this purple line. So I get 2 graphs. The outside graph, the thing on the outside, I claim it is a recurrent graph. Why is that? The carrier, so firstly, it's not a triangulation, right? Because here I have circles that I cut them, so they're not here. But the same argument with resistances work, right? If I look far enough, it is a triangulation, and then the resistance between an annulus of radius 1000 and then twice 1000 is at least a constant, and you can repeat the same argument. So the outside graph is recurrent. Why is the graph inside also recurrent? Yeah, I take an inversion around that point. An inversion sends circles to circles. So what I get is after I invert the outside map, the inside graph looks the same, right? It's also a graph that covers everything except for some bounded space in the beginning, and you can use the same techniques to show that it is recurrent, right? So if we have the statement about the shape of the circle packing being like this, then we get recurrence. So the purpose of this lemma is to show that indeed when you circle pack finite graphs and choose a random point, right, and look around this point, what you get by look around this point, I mean I choose a random point of my finite circle packing, right? I take this I take this random vertex, I put it as a circle of radius 1 in the origin, and take a limit. I take a limit using compactification. My goal is to show that what I get is almost surely circle packing in which its carrier is either R2 or R2 minus 1 point. Okay, and this is the purpose of the lemma. Okay, and this is how we're going to use it, and it's not going to be entirely clear from the statement why it is like that. Okay, so let's go back now to the statement of the lemma and forget everything else, just so we can keep everything in one point. So we have a set of finite points. Okay, these eventually will be the centers of the circle packings of Gn. So we look just at the centers of the circles. It's a set of finite points. It has cardinality n for each finite graph. We defined our isolation radius, and now the complicated definition is going to be the following: given delta in 0, 1, and an integer s bigger than 2, we say that W, a point in C, is delta S supported This is the definition. If, let's say it first in words, if the disk of radius delta minus 1 rho w, so a large disk, delta, we think about delta as small and S as large. We look at a large disk around the point, much larger by some multiplicative constant, but large constant of rho w. If the disk of radius delta minus 1 rho w contains at least S points. So if this was just this definition, this would have been easy, but with the further condition, outside any other disk, any other disk of radius, of a much smaller radius, radius delta times rho w. Delta times rho w. Okay, let's, this is the definition. Let's write it first in, just in a formula so that it will be clear what it means. This means, or the infimum over all the points in R2 of the intersection of the cardinality of all the points that are in the Euclidean ball. So this is now Euclidean ball. Euclidean ball around W of radius delta minus 1 rho W minus the ball around P, some arbitrary point that we're taking the infimum of a much smaller ball, delta rho W. All of this cardinality has to be bigger than S. Okay, this is was not just hard to define, not just hard to understand, but also hard to write. Let's see an example. So, for instance, let's look at this point, and let's assume our set looks like a point here, next to it a point, and a lot of points that accumulate this is a finite set, but they get closer to something like this, right? So now the claim is that this point is not delta S, and let's say this distance is some constant, Shall I draw this bigger? Yes, I think so. Let's draw this bigger. I have 1 point here, 1 point here, 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 and so forth, and many points in here. And I look at this set, and delta is something. So this distance is 1. This distance is 1, and this distance is 10. Right? And s is a giant number. S perhaps is square root of the number of points inside. So this point, and I look at, for instance, delta equals 1 over. Let's switch colors. And I look here at delta that equals 1 over 10. Right? So, and I look at this point. So in order to check the definition, I have to look at the ball of radius 10 times 1. The ball of radius 10 around this point. So this will be this ball. Right? Containing almost everything. Right? And I have to have at least s points there. So if n is the number of points, let's assume s is, I don't know, n over half or square root of n, a lot of points. So even though this ball contains many of the points, just the fact that most of the points are located in one small neighborhood, right? I could put here a ball of radius 1 over 10, right? So this will be delta times rho w. So I have a point here in which if I remove, right, this is radius 1 over 10. If I remove this point, then the number of points that I see inside the big ball is only going to be 1, 2, 3, 4. Right? And not all of the points, because the points I made them closer and closer to each other in some geometric fashion. Right? So this point, even though in its ball has many, many points, right, it is not delta S supported. Right? But on the other hand, if we have taken the mirror image of that and take a union, so here I'll have more points, and here I will have many other points, as S, and S is taken to be something like n over 2 or slightly smaller than that, then this point is delta S supported, right? Because the big ball contains these points as well, and if I remove this little ball, I still have many points here. And if I remove this little ball, I still have many points here. So no matter what I do, right, no matter what I remove, I see in the big ball many points. And the statement of the lemma is going to be, there cannot be many delta S supported points, right? And why is this? Right. So this is the perhaps let's state it. So far there was just a definition. So the theorem is as follows. Theorem: there exists an A such that for any delta between 0 and 1/2, so we think about delta as small, and any C finite set of points and any S integer bigger than 2, the number of delta S supported points is no more than A C delta to the minus 2 log of 1 over delta divided by S. And the way to, so this is the statement. And the way to think about this lemma first is to think about delta as a small but fixed number, and S to be something very large, which may depend on the number of points. For instance, if S is a square root of the number of points and delta is something fixed, then you see then the number of delta S supported points cannot be more than some constant times square root the number of points. Right? So if we choose randomly such a point, we will not choose a delta S supported point. Okay, so before we start the proof, let's just see that this is indeed the kind of behavior that we want to capture, right? A delta S supported point means not only that you have to have many points, right? That they have to be spread out enough. So if I remove here many points, I will always have more. So you see from this picture that in this picture, a delta S supported a delta S supported point can be such a point in which you have one accumulation point here and one accumulation point here, right? If this was if I would have continued and to add more and more points, right? From this point, it would look like I have two accumulation points, right? One here and one here. And the statement of the lemma says, if I choose a random point, it will not look like that. In fact, in this sequence of points, if I choose a random point, it's very likely going to be one of the points inside here. And from one of the points inside here, the picture looks completely different than it is from here, right? From the point at the very end, it looks like something like this, right? You have one close point of distance 1, right? Or and the other is a distance 2, and so far and so on. And you could check, it's very easy that this is not a delta S supported point for the usual choice of delta and S. All right, so at least from the statement we see that this is the kind of estimate that we want. There cannot be many points in the plane, inside a finite set, that if we put ourselves in this point and look left and right, then we see something that from our point of view looks like two accumulation points. Okay, are there any questions about the statement? Shall we see? Yeah.
To the power of minus 2, is that for the C or for the delta?
This is for the delta. For this class and perhaps next one, all that we're going to care is this is some constant depending on delta. But when we start talking about random planar maps, it will be important that we have a polynomial bound here on delta. So this will play a role. I'm presenting it like that just for our future use. Okay, so you can, if you are also want to convince yourself that this is true and check it on a few examples, you could check it on the drawing of the binary tree of height n, right? The usual drawing in which every time the edges, their length becomes smaller by some factor, right? And so on. And at the bottom, you have 2 to the n leaves, 2 to the n leaves, which are 2 to the minus n separated, right? So here I have an actual drawing. If the vertices of the binary tree are my set of points, not just the leaves, everything, and I choose S to be of order n and delta to be some constant and large, you can convince yourself that only the topmost vertices are going to be the delta S supported points, and the rest of them are not. So it fits exactly. And in fact, this lemma is tight except for this log. And you should also convince yourself that if you look at the points of the square lattice, for instance, on n by n square lattice, there are no delta S supported points for S being large and delta being some small but fixed constant. Right? So when you perhaps play with enough example, I don't have an answer to how did they think about this lemma. So this is and many other things I could tell you what was the thought. This I don't know. My only guess is that they tried many examples and saw that there was some sort of behavior and continued from there. Okay, so the proof of the lemma, perhaps well, it's a theorem, but I'll prove it in 2 parts, and let's just do the first part today. That will show you the kind of arguments that are needed. For that. I'm afraid I'm unable to keep all the definitions on the board, so I will erase this part to begin with. So part 1 of the proof. So the first claim, which already gives you something that looks very similar to the statement of the proof, and let me tell you what it is. So part 1 of the proof. As you can see in the notes, the proof is not very long, but it's a very, very clever proof. So I'm going to make now a different statement that you can ignore everything else, and there will be no delta, but there will be there will still be S. So fix k some number bigger than 3, And let G0 be a tiling of R2 by, what is it, 1 by 1 squares. Right, so this is just, I look at the, not on the lattice, I look at the actual squares. Right, I just split all of R2 to squares. And then G2 is going to be, sorry, this was G0. G1 is going to be K by K tiling on top of G1, on top of G0. So if K was 2, okay, then I would take, or if K was 3, I would take, right, these squares, and this would be 1 square, and here I would have another square, etc., etc. So I have a tiling on top of the original tiling that goes up, and I'm also going to look at tiling that goes down. So I'm also going to look at G minus 1, which is going to be 1 over K by 1 over K tiling. So all of these tilings are an infinite collection of squares, right? And so here I will have, in each little square, I will split into K by K or 3 by 3 in the picture square. So this would be a reduction. We will reduce the lemma from this from the following statement, and so we have our set of points, right? So we have this hierarchical collection of squares, right? Put on R2, and inside we have all sorts of points that belong to our set. Okay, and the statement is, and we say that, or so the definition is, sorry, we say that a square S and Gn. So I'm emphasizing again that all of these tilings are canonical, right? They're nested inside each other, right? So a square S and Gn is similar, is S supported, right? If the number of points in it, C intersection with S. So this is big S and this is little s. I apologize for that. This big S for a square, and this is little s for the integer from before. So we want the square to have many points inside, but not only many points, also if we erase any other of the square below it, one of the squares below it. So if S, C intersection with S minus S prime is bigger than little s for any S prime, right, that belongs to Gn minus 1. And n can be anything, not just a positive integer, but also in Z. So this would also correspond, without any caring about the scale that you are. Okay, so I have to, if I have inside this big square, so it's a very similar definition, but it's suited for this particular. So if I have here inside this, if I have inside this point, if I have inside the square many points, but such that if I remove any of the subsquares, I still have many points, then I call this big square S supported, right? And the statement is as follows. Right? The claim is, of course, as we can expect, there cannot be too many S-supported squares. So the claim is the number of S-supported squares is no more than twice times C over S. And here it is little s. Okay? So notice that this is a slightly different statement than the lemma, but it is very similar. And it's weird because we're looking at an infinite set, a countable yet infinite set of squares in all scales. And some of them we mark as S-supported, right? It has many points inside, at least. So firstly, it's clear that this set of S-supported squares is finite, right? You cannot have too many, because once you have a giant square in which all the points look like very, very small, this cannot hold, right? Because you remove this one of the squares that contain them, and you're not S supported. And also, if you have a teeny weeny square that doesn't see any points, or perhaps just one point, it of course cannot be S supported. So even though this is a statement about infinite tilings, this is in fact a finite statement here. What is the proof? So let me convince you. The proof is in your page 52, and it's a formal proof. But let me tell you what the proof is just by hand waving. All right. So the first thing that we could do, and we imagine that the squares are so that like no point is just on the boundary of each square. Right. There are countably many. The measure of all the orange line is 0, so we can always move it so no point is just precisely on the line. And now we have this tree structure here, right? We have a tree structure in which the biggest square that contains all the points, right, is the root of the tree, right? And all of its children are the subsquares of it, only if there's a point inside. If this is empty, then I don't draw a line, right? So if I have, so the big square is a one vertex, and its children are only going to be the ones that have points inside, right? And then you reach the bottom of the tree, which are all the small squares, right? In which they may contain at most one point, right? And every small square that contains one point, at most one point, or exactly one point even, because it's the most bottom one, this will be a leaf of the tree, right? So you have this tree that somehow represents this picture. And in fact, this tree is inspired by this tree, because in some sense, this is the hardest example for the lemma. So here, how do you prove the statement now? So this is a very nice trick. So you have this tree that you represent, that each vertex correspond to a square, right? It's rooted, so the topmost is a giant square, right? And it grows deeper and deeper inside. You can even imagine this tree somehow embedded in R3, right? Something like that. And then at the bottom here, I have a very fine squares, right? And I erased all the squares that don't contain any vertices, any points of the plane. So the only leaves that I have are square that contain one point, or something like that. And now at the leaves, I put at the leaves of this tree, at each point I put a marble. Yes? Do French people know what a marble is as well? Or it's a particle, a golf ball, whatever you want. Right? So all the leaves at the bottom, all the leaves that are at the same height of the tree, right? They all have a marble, and I am performing the following operation. Each vertex, each leaf is going to send up its marble to its father. Right? So now I have the father of one leaf will receive a marble from its son, but perhaps from other leaves that it has. And then all the leaves sent their marbles one floor up. And now I continue. Now that all the people, all the vertices of the tree that have received one marble or several marbles will send their marbles back up, to their father. And so on and so on. And I continue doing this. If I do this, right, I began, the number of leaves was precisely the number of vertices. So in the beginning I have n particles, n marbles, and they go up and up and up. And as I finish this procedure, at the top I will have exactly n marbles. Okay, so this is should be clear. And now I'm going to change this procedure a little bit. And I'm going to do it so that I'm going to change the rule so that if I'm a vertex in the middle of the tree, right, and I received some amount of marbles, and I want to send marbles up to my father, and I'm doing it with the following rule. If I want to, I never send more than S over 2 marbles up. So if I received from my children this enormous amount of marbles, so for instance, perhaps I received S or 3S or even more than that, the rest of I send to my father S over 2 marbles, and the rest I collect to myself and put in my pocket and never return, right? Right? So is the operation clear? And then eventually at the top, the grandfather, the great-grandfather of all of the leaves is going to receive the amount of marble that is smaller than the total number of particles, because some of the vertices in the tree were greedy. Okay, so this, yes, question?
Tiny remark. So you have to choose your origin when you make the grids, so that all your points are in one.
Yeah, or if you look at if you look at even top, then you will have a tree that has like just one child. If you look at something bigger, and that's also fine.
So if your points are on the 3 different quarters distributed, then you will not have one father, strictly speaking.
I don't understand. What do you mean? If the points are here, 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 and here.
No. That's your origin, where the white at the
the origin of the tree, the root of the tree is the biggest square.
No, the origin of your grids.
Yeah, so I didn't specify the origin of the grid.
The origin, you have to choose the origin of your grids in such a way that all your points are in one quarter. Otherwise, you have not a tree in the end, but
there's always a square that contains everything, because you have infinitely many levels.
Yeah, but as you define,
So if
you take 4 points on 4 different.
If I have 4 points here, 4 points here, 4 points,
Only one, and
1 and 1, right?
and 1, then you will not have a big.
I will have it. In this case, I will have a tree that looks like this,
Not quite.
right?
All your squares, as you define your grids, all are.
Okay, let me finish the argument, because this is you interrupted me in the middle of the punchline, right? So I'm reminding you, you have the particles go up in the marbles, and if you receive more, if you want to send upwards, you have more than s over 2, you only send s over 2. So you concatenate the amount that you send upwards. And now let's see what happens when you have a delta S supported square, right? So the number of original marbles that you have, the number of marbles is exactly the number of points, right? So now you have this tree, right? And this is a vertex of this tree, and it goes on, and this goes even more, perhaps. Perhaps some of the vertices have only one child up, and so on. So there's more thing going down here and up here. But this point corresponds to a S-supported square, right? So this point corresponds to something in which you see S points here, right? And you continue seeing S points no matter which small square you remove from inside. Right? So let's observe that there are several things that can happen. Right? So assume that none of these squares have more than s over 2 points inside. None of the small squares. Right? This will mean that you have. This will mean that from each of these vertices you get less than s over 2. Right? But you know that. So none of them were greedy and ate the marbles. Right? None of their children ate any marbles, and so you get at least s points into you, right? So you've eaten at least s over 2 points, right? So my claim that I'm trying to convince you is that every s supported square eats or hides or whatever, eats at least s over 2 marbles. So if none of the subsquares have s over 2, you are the amount that you get is at least s, because you're s supported, and you eat s over 2. Let's say one of these things, right? One of these points, one of these squares do send you s over 2, right? So perhaps it ate some of the marbles, and it's not giving to you all of them, it's hiding them. But you know that from the rest of them, you do get at least s, right? So if you have only one, so this one sent to you s over 2, right? And the rest of them had to send at least s, right? Because I assume that precisely one square is such that precisely one of your children ate your marbles. So from here you will get at least s over 2, at least s from all the rest, because you're s supported. So the amount that you eat in this case is at least s marbles and not s over 2. Right? In the other situation, you have that you have more than one child that ate your marbles, right? So this one perhaps, and a few more that 8 marbles, but at least 2. That means from this one, and from this one, and from this one, you will get precisely S over 2. Right? They were greedy, but if they are greedy, they're still giving you a lot of marbles for your own collection. So if you have at least 2 of them, you will receive at least S, right, marbles from them. Right? From this one, you'll receive S over 2, and from this one, you will receive another S over 2, and from the rest, you don't really know. So each S-supported square eats at least S over 2 marbles. The total amount of marbles is the size of the point set C. So there cannot be more than this amount, 2C over S, of S-supported squares. I'm practicing my freeze. Right? And this is the end of the proof. We'll continue the proof of the lemma and its consequences on Monday. Thank you very much.